So how on earth do we teach a machine to understand and generate human language? I mean, it's one of the biggest challenges in all of artificial intelligence. But the solution, believe it or not, starts with a concept that's both surprisingly elegant and, yeah, deeply mathematical. Okay, so here's the central puzzle, right? How can a computer write a completely new sentence, one that doesn't exist anywhere in the billions of pages it was trained on? It honestly seems like magic, but it's actually a really clever application of statistics.
You see, here's the trick. We don't teach the machine to be a novelist right out of the gate. We reframe the whole problem into a much more manageable task. Instead of asking it to write a sentence, the goal just becomes predict the next word. That's it. If a machine can get really good at just that, one word at a time, eventually it can string those predictions together into something that looks like a coherent thought.
This quote really just nails the whole idea. These models, they don't truly understand what they're writing. They've simply been shown this massive feast of languages and have gotten really good at identifying the patterns, the scraps of how we humans connect words together.
So how do they learn these patterns? Well, it all starts with the fundamental building blocks of this whole language machine, a concept called N-Grams. And this is where that magic we talked about starts to look a lot more like simple counting. First things first, before a computer can analyze anything, it has to break a sentence down into pieces it can actually count. This process is called tokenization. All we're doing is taking a stream of text and splitting it into individual units, or tokens, which for our purposes today are basically just words.
To walk through this whole process, we're going to use a super simple classic example sentence. The cat sat on the mat.
Okay, the simplest form of an n-gram is a 1 gram, also called a unigram. And this is, well, it's just a list of all the individual words. There's no sequence, no context. It's pretty much just a bag of words from our original sentence.
Now things get more interesting when we step up to 2 grams or bigrams. Now we're no longer looking at single words. We're looking at pairs of words that appear next to each other. The cat, cat sat, sat on, and suddenly you can see a little bit of structure emerging. We're starting to learn the relationships between words.
So this is the crucial point. As we increase the n in our n-grams, going from unigrams to bigrams to trigrams, which are groups of 3 words, we are feeding our model more and more context. And that context is absolutely everything when it comes to making intelligent predictions. Okay, so let's dive into the engine room. How does all this counting actually turn into a prediction? The beautiful part is that it's not some crazy, complex calculus. It's really just a game of chance, powered by simple counting and probability.
The whole system really boils down to this one central mathematical idea: conditional probability. We're just asking a specific question. Given the words I've already seen, what is the statistical likelihood, the probability, of any given word showing up next? In math notation, it looks like this. We want to find the probability of a specific word, and that vertical bar in the middle just means given the preceding words. So it's the probability of an outcome based on what we already know. And the calculation itself, it's surprisingly straightforward. To find the probability, you just count 2 things from all your text data. First, count the number of times the full phrase appears, and then divide that by the number of times just the context, the first few words, appeared. That's it. It's just a ratio. Let's use a real example. Imagine our model has scanned a ton of text, and it finds that the phrase "the cat" appears 100 times. In 80 of those cases, the very next word was sat, making the trigram "the cat sat." And in the other 20 cases, the next word was ran. Okay, so let's apply the formula. If the model sees the context, the cat, what is the probability that the next word it should predict is sat? It's just 80 divided by 100, which is 0.8 or 80%. And just like that, the model now knows that sat is 4 times more likely to follow the cat than ran is. That right there, that is the core of the predictive engine. It's that simple. So we can predict one word, but what happens when you chain these simple probabilistic predictions together, one after another? What kind of text do you actually end up with? Check this out. These are actual sentences generated by these models. On the left, the bigram model, which only has 1 word of context, just produces pure gibberish. It's a word salad. But look at the right. The trigram model, with 2 words of context, generates a sentence that is so much more coherent. It's not perfect, but the structure is there. It just goes to show you, more context leads to better quality. But, and this is a big but, N-gram models are just a starting point. they have some serious fundamental flaws that stop them from creating truly human-like text. So let's look at the cracks in the foundation.
Here's the Achilles heel. Language is practically infinite. What happens when the model comes across a totally valid combination of words that it just never, ever saw during its training?
While the consequence is catastrophic, if the count of a specific n-gram is 0, then its probability is 0. The model basically hits a wall. It has no information to make a prediction, and the entire generation process can just grind to a halt. This is often called the zero-frequency problem.
And this problem gets even worse because of something called the curse of dimensionality. We know more context, a higher n, is better. But as n increases, the number of possible n-grams grows exponentially. There are just too many combinations. Even with all the text on the entire internet, you'll never see every possible 5-gram or 6-gram. The data becomes incredibly sparse, which makes that zero-frequency problem almost guaranteed to happen.
So let's just do a quick recap. N-grams predict the next word based on the few words that came just before it. They work by calculating simple probabilities from word counts in a huge amount of text. A larger N gives you more context and better sentences, but it comes at a cost. And crucially, these models are brittle. They really struggle with new phrases and just the sheer scale of language.
This leaves us with a pretty deep final thought to chew on. We've seen that the basic rules of putting a sentence together can be modeled with simple probability. And these fundamental ideas are the direct ancestors of the giant AI language models we have today. So, if language can be so effectively modeled by statistics, what does that tell us about the true role of human creativity? It's something to ponder. Thanks for joining me.